In this video, I'll be demonstrating some advanced features of TransAT by showing a simulation of a flow over cylinder. If you have not already done so, it would be helpful to view the tutorial, Flow over Backward Facing Step. Our flow consists of a cylinder and a free stream velocity of 0.015 meters per second. The cylinder has a diameter of 1 meter, is 4.5 meters away from the inlet, and a 12 meter wide domain. The domain has symmetry boundary conditions on either side, and the exit is prescribed with a pressure boundary condition. The results of our simulation are shown here. I've plotted the pressure contour and the velocity vectors. Our fluid has a density of 1 kilogram per meter cubed and a viscosity of 1 e to the negative 4 Pascal seconds. The flow has a Reynolds number of about 150. The outcomes of this tutorial includes to learn how to add objects. We will use the Immerse Surfaces tool, and we will adjust the properties of an object. Additionally, we will define various types of meshes. We will make a standard grid mesh, and we will use the BMR tool. Here I have shown a comparison of a standard mesh and a block mesh refinement. You can see here in the standard mesh, a refinement is created all around the object. This results in defined cells even far away from the object. Alternatively, you can use the block mesh refinement to specify a specific area where the cells will be refined. This reduces the number of cells required for the simulation. These will be the goals of our first and second simulation in the tutorial. Our third simulation will be a flow over a hot cylinder. We'll repeat the simulation, but add a 500 watt heat source for our cylinder. Now let's begin our setup. To begin, we will create our project files. I will create a directory for the simulations we will be running for our cylinder. We will be running a total of 3 simulations: the standard grid, the BMR mesh, and the hot cylinder. And additionally, I will create a template directory. We will create the template first and then copy it to our 3 simulations. The first step is to create our cylinder. We will define a base coordinates, the radius, and the length. Additionally, the points on the cylinder. Once it's created, we'll notice it is not oriented correctly. Let's fix this. We'll select our cylinder and rotate it in the Y direction. Next, we will translate it to the location in the flow we desire. And we can refresh the view. Now that the cylinder is created how we would like, let's export it to the mesh. We will be warned that our mesh will be reset. And we will define units for the object to be input into the mesh. And finally, we will be confirming to resize the domain. Next, let's go to our mesh. We will define the size. For our 2D problem, we'll set up coordinates in the Z direction. And for now, we will not define any cells. This will be done once we copy the template into our standard mesh and our BMR mesh. We will also skip creating blocks for now and do this later. We will go to boundaries and create our boundary conditions. We will define a constant velocity boundary condition of 0.015 meters per second and a pressure-based exit condition. Next, we will assign the boundary conditions to the surfaces. And we are finished with the domain setup. Let's save. We are prompted with a warning that we have not selected immersed surfaces. We will click Continue. The immersed surfaces are in the Input tab under the Advanced Models. This will be automatically selected anytime you have an object in your flow. We will define our basic equations of pressure and our velocity for our 2D flow. We will also define reference properties for non-dimensional numbers. Now we will define our phase. And we can continue on to simulation parameters. We will have an unsteady simulation with a total time of 10,000 seconds, although we will have a max number of time steps of 4,000. Under advanced options, we will set the initial time step to 1 second and keep it at 20 iterations per time step. We will adjust the auto relaxation factor to 0.83. Under adaptive time stepping, we'll adjust CFL limits between 0.7 and 1, and diffusion between 1 and 2. Under equations, for all quantities, increase the convergence tolerance to 1e⁻³ . For advanced solver options, other variables, confirm BMR iterations are at 5, but for pressure, we will change the BMR iterations to 15. Under initial conditions, adjust the U velocity to 0.015 and the remaining variables to 0. Finally, under output management, we'll format the output to pair view every 100 time steps. We'll double check that pressure, U and V velocity are outputs, and that non-dimensional numbers are calculated. This finishes the setup of our templates. Let's continue first from our templates and set up the multi-grid or the standard mesh. We'll go to Files and save our project as a new name. Under our directory, we'll save it in the multi-grid folder. From the template, the simulation is all set up except for the mesh. We need to define our domain and grid cells. For the discretization, we'll define 69 in the X direction and 49 in the Y direction. Because our problem is two-dimensional, we'll set one cell in the Z direction, or a discretization of 2. We'll change the ratio to 1. Under blocks, we'll be splitting to 4 blocks. Now, under the mesh info in the right-hand corner, we can look at some information about our mesh. At the bottom, we see that our total number of cells is a little over 3,000. This concludes the setup of our multi-grid mesh. Next, we will set up the BMR mesh. We will go back to our templates and we will save as again. Under our domain and grid, we will be defining a slightly different number of cells. But again, the problem is two-dimensional. So our number of cells in the Z direction will be 1. Under blocks, instead of splitting, we will now be adding a sun block. This is the BMR tool. We can define a region where the cells will be refined. We can use sliders, or additionally, we can enter in our coordinates. For our x-min, we'll split it from 3 to 10, and in the y coordinates from 4.5 to 7.5. With our block regions created, we'll notice that we have two blocks. The coarser the block, the lower index number it is given. We will be now splitting the coarser block. If we look at our mesh info, we will notice now we have reduced the number of cells to 2,000. The BMR tool is a good way to keep a fine mesh in important areas, reducing the number of cells greatly from the standard mesh. Let's save our project, and we are finished with the BMR mesh. Now we can begin to set up our third simulation. We will begin our third simulation from the BMR setup, so we will go to Files, Save As, and select the directory of our hot cylinder. Under Input and Physical Models, we are now adding temperature to the basic equations. Under our mesh and objects, selecting our cylinder, we can define our properties for the object. Let's make sure the density is at 8,000 kilogram per meter cubed, and we'll set the temperature parameters. For a temperature model, we'll use conjugate and a heat source of 500 watts. Under the Input tab again, we'll go to the phase properties and define the thermal conductivity, thermal expansion, and heat capacity. Lastly, under initial conditions, we'll set the temperature at 300 Kelvin. This concludes the setup for all of the simulations. You can now execute them as you wish. With the simulation of the hot cylinder finished, I will briefly show the results. With PairView open, I will load the results file under My Documents. In the results folder, I will look for the VTM file and apply. I am interested in the surface of my simulation, and I'm interested in temperature. I will press play to view through the results. But after noticing the results play, my scale is not adequate. I will skip to the end, and I will rescale. Now I can go back to the beginning and play my results again. This concludes the tutorial of a flow over a cylinder.